Hello everybody, how's the life? Seriously, I want to kill my boss right now, but anyway, that's not the point, huh? Okay, we need to embrace the technology. Anyway, electrolysis tends to fill people with dread, something like exactly. So now we're gonna overcome this, right? Okay, so let's move on with our life. Okay, but before we begin, okay, you need to have pen and paper beside you, okay, because we're going to work through some examples together. Okay, chemical series. Okay, if you do not have electrochemical series, please, okay, again, copy down the electrochemical series now, okay, and pause the video first. Now let's move on. So some basic introduction. As you all know, electrolysis provides evidence that, okay, a compound, okay, is made of two or more elements. Okay, is powered by DC power supply, right? Okay, the positive electrode is known as the anode, okay, negative electrode cathode, and the electrolyte is the solution or the molten compound. Okay, so anyway, let's move on. The key point that you all need to remember is always cation, positive, goes to cathode, negative electrode to gain electrons and hence be reduced. Okay, similarly, anion goes to anode to lose electrons and be oxidized. So fast so furious. Okay, anyway, there are four main scenarios that we'll be looking at today: molten NaI, okay, dilute sodium iodide, concentrated, and with electrode participation. Okay, so let's go to the first. Okay, so now first of all, okay, if the ions are in a solid state, NaI solid, right, electrolysis will not take place because the ions are not free to move. Okay, so what happens when they're in a molten state? Okay, as usual, please remember cation go to cathode to gain electrons, anion go to anode to lose electrons. Alright, okay, so let's see what happens. Okay, so electrons come out from the battery, okay, to the cathode. Okay, so of course, okay, the cations are attracted to cathode and ions are attracted to anode, right? So at the cathode equation, okay, you have your Na plus plus, okay, E minus to give you your Na liquid state. Why is it in a liquid state? Because it's molten, temperature is very high. Okay, so when the sodium atoms form, okay, they become liquid sodium, okay, and they fall to the bottom, okay, of the whatever this is called, beaker or chamber. Okay, anyways, let's move on with a life. Okay, at the anode, okay, the iodide ions lose electrons, okay, to become, okay, iodine atoms. But since we do not put, any, okay, negative sign in the equation, you have noticed that I kicked the electron across to the other side. Now, the other key point to note is that iodine atoms on their own are not stable. Okay, so therefore they will form a diatomic molecule and the equation will hence look like this. Okay, so anyways, okay, now how do we write an overall equation? Oh, sorry, forgot, okay, the animation. Okay, now how do we write an overall equation? The key idea is that the number of electrons on the left must be equal to the number of electrons on the right. So what do I mean? Okay, so now at the cathode, okay, you can see that, okay, it only requires one electron, okay, while at the anode it requires two electrons, right? So therefore, okay, we need to balance off the electrons by multiplying the cathode equation by 2 to get 2 Na plus 2 E minus to give you 2 Na liquid, right? So once this is done, okay, we can actually cancel off, okay, the electrons on both sides and put them together like a simultaneous equation, right? And so this is how we get, okay, the equation for the overall reaction. Okay, so of course we're definitely going to have some practice. Okay, so I suggest you pause the video here, okay, while you work out the solutions on a pen and paper. Okay, solutions will be provided soon. Okay, so you get the solutions here. Okay, so anyways, we need to move on with a life. Okay, now how about if you add water to a solution? When it's dilute any iodide solution, okay, regardless, okay, of whether it's concentrated or dilute, there are always H plus and OH minus ions due to auto-ionization of water. So a nifty trick I like to do is, okay, some rough working here. Okay, so here I'll put in all the ions that are present. Okay, so first of all, you have your sodium ions and your iodide ions. Okay, then, okay, because there's water present, okay, there's going to be H plus and OH minus. So here's where the electrochemical series comes in. You have to ask yourself, right? Okay, who will be preferentially discharged? Okay, in the presence of, okay, H plus and Na plus at the cathode. Of course, sodium being more reactive, okay, has less tendency to gain electron. Hydrogen less reactive, higher tendency to gain electrons, so hydrogen will be discharged here. Okay, and so this is the equation that you get. Okay, now between the hydroxide and the iodide ions, okay, as you notice, okay, hydroxide will be preferentially discharged according to electrochemical series. Okay, so now how do we write the overall equation? Okay, so it need a couple of steps again. Okay, so again, key idea, okay, number of electrons on left must be equal to the number of electrons on the right. Okay, so at the cathode and anode, again, you notice that at the cathode there are only 2 electrons, so at the anode there are 4 electrons. So of course the cathode equation must be multiplied by 2, okay, to give you something like this. Okay, then, okay, you can start cancelling, okay, away the electrons and put together the main equation. Now, you would have noticed that, okay, I actually combine a H plus and OH minus together. Okay, this can be done because both of them, okay, are actually being discharged, okay, from the same substance. In other words, the same water. Okay, this one will become more clear as we look at the next example. Okay, concentrated sodium iodide solution. Okay, oops, sorry. Anyways, I forgot, right? Okay, because there are 4 water here and 2 water on the other side, okay, so our equation cannot be done yet. So what we need to do is, okay, we need to again cancel off the common factor. So this will give you 2 water molecules on the left. Okay, and so this is the final version of the equation. Alright. Okay, let's move on to a slightly more couple, okay, with concentrated sodium iodide solution. Now, even though it's concentrated, okay, there are still water molecules present, so therefore there will still be H plus and there will still be OH minus. Okay, now, because the difference in the reactivity between sodium, okay, and potassium is too large, okay, so even though the solution is concentrated with a lot of Na plus ions, overall, okay, the H plus ions will still be discharged preferentially. Okay, so what I did here, okay, was actually I put in the arrow, okay, the pink arrow, okay, to represent that the concentration, okay, has increased, okay, for the Na plus and the I minus ions. Okay, so now as I was explaining, okay, even though, okay, the sodium ions, okay, have higher concentration, but because the difference in the reactivity is too great, okay, so therefore, okay, overall the H plus ions are still being discharged. Okay, now for electrochemical series, okay, the cation portion, okay, if the solution is concentrated, cations all the way until zinc, okay, can possibly be discharged. Okay, anything above zinc, things like aluminium, magnesium, etc., will never be discharged no matter how concentrated the solution is. Okay, however, okay, for O levels, they do not tend to test, okay, on cation so much. Okay, so this part is not so important. Okay, the more important one is what happens, okay, in the anion section. Okay, now for the anion section, you notice that the position in the electrochemical series is not too far apart between OH minus and I minus. So therefore, when the solution is concentrated, okay, the I minus can actually be, okay, discharged preferentially. So in this case, okay, the equation that you get is the iodine ions being oxidized to form iodine molecules. Alright, now again for your electrochemical series, okay, all the anions, okay, can be discharged except when the solution is concentrated, except for, okay, the sulfate ion and the nitrate ion. Those 2 ions are never discharged no matter how concentrated the solution is. Okay, so now the part that you guys love, okay, how to write the original equation. Okay, so for the original equation, okay, we need to do a little bit of working. So as usual, key idea still the same. Okay, at the cathode, okay, 2E minus, okay, anode 2E minus, so that's great. We don't need to do any more balancing. Now, but you notice that we have actually taken out, okay, ions or discharged ions from 2 parts, okay, of the thing. So therefore, we cannot just write the equation as we saw earlier. Okay, so what we need to do is, okay, because H plus comes from water, so one water molecule gives you one H plus and one OH minus. So you got 2 H plus here, so we need to have 2 water molecules. So you got 2 water molecules that will give you one H2 gas as well as 2 hydroxide ions. Okay, for the other part, okay, we need to add in the iodide, right? Okay, so iodide comes from NaI. Okay, so again, I got 2 NaI, Okay, so therefore this is what I should write. Okay, now you notice that you got 2Na plus and 2OH minus aqueous, right? So therefore this will be written simply as 2NaOH equals. Okay, so now let me pause here for a minute. There are some key observations that you need to take note of. Okay, first of all, you will notice that the solution becomes more alkaline, right? Because the H plus ions are actually being discharged at the cathode, leaving behind the OH minus ions, which you can see also from the overall equation. Okay, now another possible observation that you might make is that the solution will actually turn brown in color with a black deposit. That's because of the iodine form. Now, some of you may ask, what's the state symbol of the iodine? In this case, the state symbols always depend on the temperature. For solutions, what we tend to do is that we tend to have the crap, forgot what I was trying to say. Now for solutions, the temperature doesn't then tend to be that high. So therefore for iodine, it will still remain in either the liquid or solid state. So but since iodine is able to dissolve into water, so therefore I put an equal state symbol at the back. Alright, but if it's chlorine gas that you're discharging, or fluorine gas or something like that, you may want to put gas at the back instead. So anyways, let's move on to some practice questions. As usual, get out your pen, preferably glitter and paper, work it out, and the solutions we provided. So you should pause the video here. We get some new answers. So the answers are here. Again, compare them. Now I'll explain two of them. Electrolysis of dilute CuCl2 and of concentrated CuCl2 for those who need more help. For those who do not, you can skip the next few minutes. Now for the dilute CuCl2 solution, again, always take note of what's at the cathode and what are at the anode. So therefore, since copper is less reactive than hydrogen, copper will be preferentially discharged. So therefore, this is what you have. Now, because the solution is dilute, therefore the OH minus ions are preferentially discharged. This is what you get. How to write the overall equation? So as usual, you can put down the equation at cathode anode. Now what do you notice? You notice that again the cathode is short of electron, short of 2. So everybody multiply by 2, you get 2Cu2 plus 4E minus to get 2Cus. So again, how do we write the overall equation? Because the 2Cu2 plus come from the CuCl2, so therefore we need to put 2CuCl2 at the back. This will give you 2Cu solid and 4Cl minus. Alright. Then next, for the water portion, the OH minus ions come from water. As you remember, each water molecule give you 1 H plus and 1 OH minus. So if you've got 4 OH minus, you need to have 4 water molecules, and so this is what we're going to write it in. Alright. Then again, you notice the 4 H plus and 4 Cl minus, together they can give you HCl equals. Alright, you can put them together. Then next part, you notice that you have the 4 water molecules and the 2 water molecules here. Again, you can cancel out the common factor, leave behind the 2. Alright, because it's kind of messy now, so I'm going to rewrite the equation here as a given. Alright, so let's move on to the CuCl2 solution. So in a concentrated solution, you have your increase in concentration of the Cu2 plus and the Cl minus, represented by the pink arrow again. Now for the cation portion, it doesn't really matter, because the Cu2 plus is preferentially discharged anyway. Alright. Now, but for the anode equation, because the chloride ions are high in concentration now, so instead of the OH minus ions, the chloride ions will be preferentially discharged instead. Now the overall equation is much easier to write. First of all, you'll notice that the number of electrons on left equals to right, so I do not need to do any additional balancing. Now, furthermore, both of them came from the same substance. So since they came from the same substance, right, we can just go and write it down. From the same substance, and then you get your Cu, and your Cl2. Okay, there is a balancing error there. Okay, should not need to have the 2 here, huh? Sorry. Alright, sorry about that. Move on with the life. Okay, so now for electrode ionization, okay, a key point, okay, electrode ionization only occurs at the anode, never at the cathode, because okay, all your metal electrodes, okay, except for platinum or graphite, which are inert, okay, tend to lose electrons more readily, okay, in order to form a stable electronic structure as compared to anions, which already have a stable electronic structure, and then they're trying to lose electrons, okay, so they become in a way unstable, right? Okay, so therefore, okay, whenever you see a metal, okay, at the anode, you need to be careful. Watch out for your um, electrode ionization. Okay, so now let's look at the electrolysis of dilute, okay, NaI with copper electrodes. Okay, so again, we put in all our ions present. Okay, but please remember, because the electrode is copper, electrode ionization occurs at the anode, so therefore I'm going to put copper here as well. Okay, so the choice is clear, okay, between H plus and Na plus at the cathode, so you're just going to get H plus, K being discharged. Okay, for the anode, okay, when you have competition between these three guys, okay, the metal electrode always wins. Okay, so you're going to get, okay, the metal electrode, okay, being discharged. Okay, so the metal, okay, will lose electrons, form a positive ion, and enter the solution. Okay, so what's the overall equation? Okay, so again, we have the working steps here. Okay, so again, 2H plus 2E minus K, you notice that electrons are balanced on both sides. Okay, so that's great. So that means you don't need to go and do anything else. Okay, H plus come from the water. Okay, so therefore, since you got 2H plus, you need 2 water to form H2 and 2OH minus. Okay, now the other section, okay, the Cu, okay, is also entering the solution, okay, from the anode, right? So this is what we're going to put it in, okay, and then you get your overall equation. Now, a couple of things, okay, that we can take note here. First of all, because the metal electrode is becoming the ion and entering the solution, so therefore the metal electrode will become smaller. Okay, now on the other hand, okay, because Cu2 plus entering the solution, so therefore what happens is, okay, you actually going to get a blue patch forming around the anode. Alright, because Cu2 plus ions are blue in color. Okay, now since H plus, okay, is being discharged, leaving behind the OH minus, the solution also tends to be more alkaline. Now, some of you may want to ask, why can't I write CuOH2? Yes, okay, answer is you can. Okay, if the Cu2 plus and the OH minus meet together, okay, they will actually form CuOH2, which is a solid, okay, and then you form a blue precipitate. Alright, so those are the observations that you may get. Alright, I know I'm going very fast, very furious. If you need, okay, to please feel free, pause and rewind, okay, the video and watch as many time as you need. Okay, okay, we always have some practice. Okay, so I'm sure you know what to do by now. Pause the video, okay, and try the questions first. Answers are here. Okay, so anyways, okay, let's move on with live. Okay, electroplating, okay, a spoon with silver. Okay, for those of y'all who in my class, okay, you've done this one before. Alright, okay, so now, okay, what's happening here, okay, is that, okay, couple of things you need to take note of. Okay, the electrolyte, okay, must always contain, okay, the substance that you're trying to plate it with. Okay, so if I'm trying to plate the spoon with silver, okay, the electrolyte must contain silver ions. Okay, now the material at the cathode, okay, is the one, okay, that is supposed to be plated. Okay, so therefore, if I want to plate a spoon, the spoon must be at the cathode. The anode, okay, must provide the silver metal. Alright, so let's take a look at what's going to happen here. Okay, so as usual, cations are attracted to cathode, anions are attracted to anode. Alright, okay, so electrons, okay, flow out of the negative electrode, okay, on the battery. Okay, and okay, the equation at the cathode, okay, because you have the Ag plus and the H plus, so of course the Ag plus will be preferentially discharged since Ag is less reactive than H. Alright, okay, so therefore, okay, got some animation for you. Okay, so electrons, okay, come here. Okay, Ag plus gain electron to form, okay, Ag metal, and the Ag metal is binded to the spoon, right? So this is how it gets electroplated. Now, if you carry on this process continuously, eventually you use up all the Ag plus ions in a solution. Alright, so then the electroplating process will stop. And since we do not want the electroplating process to stop, that is why the material at the anode must be the metal electrode, right? So the electrode participation or electroionization can occur. So what's going to happen here is that at the anode you got three choices, right? Your OH minus, your NO3 minus, and your Ag plus. So now, of course, you know that NO3 minus never discharge, so it's actually just between OH minus and the Ag atom. Sorry, not Ag plus, Ag atom. So because metals have high tendency to lose electrons, so at the cathode, at the anode, this is what's going to occur. So the Ag plus, the Ag atom becomes Ag plus and enters the solution. The electrons flow up the wire to the battery. Alright, thus completing the circuit. So therefore now the solution is being replenished with Ag plus ions. So therefore the reaction can continue until the anode is being used up. Let's move live. Okay, we're almost at the end. Electric cell. Couple of key points you all need to take note of. Of course, the more reactive metal has higher tendency of losing electrons as compared to less reactive metal. So the more reactive metal will lose the electrons that enter the solution. Please take note, electrons flow along the wire from the more reactive metal to the less reactive metal. The electrons never ever flow in the solution, please. So let's move on. Now in contrast to the electrolysis process, where the anode is the positive electrode, here the anode is the negative electrode. Alright, if you want to know why, I'll explain in class, but for now you can just memorize it. In electric cell, simple cell, electrochemical cell, whatever, regardless, as long as it's not electrolysis, the anode is the negative electrode. The cathode is the positive electrode. Still, cation will go to cathode to gain electrons. And the greater the difference in the reactivity of the metals, the higher the voltage generated. Alright, so we're gonna have some animation again. So first things first, all the cations are attracted to the cathode, anions are attracted to the anode. So now what occurs here is that the zinc at the anode, zinc will be discharged, and zinc metal forms zinc ion which enter the solution. The electrons will flow up through the wire all the way to the less reactive metal, in this case the copper. So this is what can happen. So you get your zinc ions with the two electrons. So the zinc ion enters the solution. The electrons flow all the way to the copper electrode. Alright. So now what happens at the copper electrode? Cations are attracted to the copper electrode to gain electron, right? So you have your Na plus and your H plus. Alright, so therefore, since H is less reactive than Na, H will be preferentially discharged. So therefore, at the cathode, you get your H plus becoming H2 gas, and of course, the hydrogen gas will escape into the atmosphere. Alright. So key point to note, as you can see here, the zinc solid electrode is actually becoming zinc ion, so the electrode will become smaller and smaller. Eventually all of it will be gone. Alright, as always, some practice questions for you. So pause the video, work it out, and then you can compare your answers after this. So the answers are here. So anyways, this part finally. So one very specific type of electric cell is actually your hydrogen oxygen fuel cell. So what happens here is at the negative electrode at the anode, hydrogen gas is being fed in. Okay, so happens is the OH minus ions, okay, from the electrolyte are being attracted to the anode, okay, where they react with the hydrogen gas, okay, to form water, okay, and electrons. So these electrons, okay, will flow through, okay, the wire, okay, all the way to the other side, okay, which is the cathode. So at the cathode, what's happening is the oxygen will react with the water, okay, and liberate electron together with electron to produce the OH minus ions. Then the OH minus ions will enter the solution again and again, right? Okay, so since you guys love, okay, all this animation, let's just give you one more. Okay, so anyway, the overall equation is as stated here. Don't worry too much about this particular example. Okay, it's a very minor part of the textbook. Okay, if you wish, you can just simply memorize this. Okay, that's all. All right. Okay, so anyways, thank you very much for listening, everybody. Okay, and participating in this monstrosity. The end. Thank you very much. Bye.